Okay, so welcome back. I think I just did a stop with YouTube and then I reopen it again. Fine. So let us start with the second topic, which is statistical tests. Okay, so the goal here in a statistical test is to make a statement, about how well the observed data is in agreement with prediction, right? So you have some observations, some observed data, and then you have some predictions. So it is a statement about the agreement. Of that, you want to formalize, you want to quantify the agreement of between the predictions and what you are observing. So these predictions are actually, so this is what you call a hypothesis. And so we would like to test this hypothesis under the light of data. And then this hypothesis is called the null hypothesis. And the notation is like H0, okay? You want to test the null hypothesis under the light of data. So for example, H0 would refer, that would refer, for example, to a concrete specification of a PDF. So I have a random variable, multivariate random variable, and then I have, imagine that this is the defined by one parameter. So this is, I don't know, some value of this theta, then that would be my H0, okay? If I have another value of theta, then that would be an alternative hypothesis, let's say, okay? Because I'm comparing the two, I will come to that right now. So for example, imagine that, I don't know, this is a Gaussian variable, and then my hypothesis is all the parameters, my null hypothesis is all the parameters defining the Gaussian variable, okay? So note here, for example, let me put an example and then make the note afterwards. So this can be, for example, mu of some parameter m. You can have more parameters here. You can have the variance of mu. So your hypothesis can be, the null hypothesis is the specification of all of these guys. Right. So what we are doing, the note is coming here. What we are doing in physics, actually, as well as in data analysis and statistical inference in general, is to estimate the mean of the distribution. So estimating this is the goal in general of data analysis in physics, in science in general, and in statistical inference. Not related to physics particularly, but to in general, okay? Okay, so how would you quantify the agreement between some null hypothesis and the data you observe? So in order to do that, so you construct, like a measure of agreement. between data and between H0 and the data, right? And this measure of agreement is called a test statistic. And this test statistic is a function of data. So, and this test statistics in somehow, I mean, this somehow summarizes the data. This is typically scalar, but it doesn't have to be a scalar. So just one number, function of all the data. So this is typically a summary of all the data you have. That allows you to say, okay, depending on the value of this test statistics, I reject, or I accept my null hypothesis. Okay. So in many situations, we want to discriminate the null hypothesis from another hypothesis, which is called alternative hypothesis. And then we call this HA from alternative, okay? This can refer to, for example, I don't know, theta equal 1, and this can refer, for example, to theta equal, I don't know, 4, let's say, whatever, okay? So you have the specification, say, my hypothesis is that the mean value is theta equal 2, and then you compare it with another hypothesis here. Then the next thing is that if your test statistics is a function of the data, then it is itself a random variable, no? Because data is random, you don't know where you're going to measure, so a function of your measurements is also a random variable, no? And will have its own PDF. And let me call this, I don't know, G of this value of the test statistic, given some theta 0. This is my H0. And HA could be another value of theta, right? Okay, so then let me, now that we are thinking in the space of the test statistic, then I can try to visualize this in a plot. So as a function of t, I can have, for example, one distribution here corresponding to null hypothesis. And I can have another distribution here corresponding to the alternative hypothesis. Right? And so what you can do here is to reject or accept your null hypothesis depending on the value of t. So here, let us talk about the significance of the test. This is defined as alpha, which is equal to an integral from some value to infinity of the PDF characterized or determined by the null hypothesis. So let me have some value here. If this is t cut, and then I have this. And then what I'm saying is that I have an integral from t cut to infinity, right? So I am referring to this tail here, and this is equal to alpha. This is alpha here. right? And then given this cut, okay, another color, but okay, let me put in green. What you can do is that if your value is at the left of the cut, then you will accept the null hypothesis. Whereas if your value is at the right, you will reject the null hypothesis. Okay. And then what is interpretation of this alpha? Interpretation of this alpha is nothing but the probability to reject H0 while H0 is true, right? And this is also called type 1 error. Okay, and this is also called, if you do this, that you reject a true null hypothesis, you are making what is called a false positive. Okay. And there is a complementary quantity or measure, which is typically parameterized with beta. This is the integral from minus infinity to t cut of the PDF given by the alternative hypothesis. So what would that be? That would be, I don't know, let me put this color. So I'm integrating over the alternative hypothesis, right? So I am like this part here. This part here is beta. So beta is another type of error, right? So beta is so-called type 2 error. Type 2 error or false negative. And it is just the probability of accepting null hypothesis while it is false. Okay. So those are like the two complementary measures of what the error that you can make when you are doing a statistical test. And then something which is very important then, and which is a function of one of these quantities, is the power of the test. And the power of the test is just 1 minus beta. Okay. So you need to, if you want, in the there is a consensus here, or there is a yeah. So you can actually fix one of the errors and then try to minimize the other. So what people do is typically to fix your type 1 error because you are fixing the significance of the test. So for a given alpha, the idea, the desire is to minimize the type 2 error. And which means the idea is to maximize the power of the test. Okay. So,
yeah?
Ryan,
I have a question. This beta value would depend on the choice of the theta A hypothesis, right?
On the choice of?
On the choice of the theta A hypothesis, null hypothesis.
Yes, exactly.
So how do you pick it to like so that it gives a real estimation of this type 2 error, because
yeah. So this is we'll see an example right away.
okay, thank you.
So I was just putting before going to the numerical example, it's just, for example, in the context of a physics application here, you can imagine that you have some data that is generated by some particle you are interested in, let's say, this is our signal, and the other data is not containing this, so that would be your background, let's say. So we want to make this test of this null hypothesis in presence of signal, let's say. And connecting with the quantities that are very common in data analysis in physics, then you can define something called the signal efficiency. So the signal efficiency is actually 1 minus alpha. And the background efficiency is actually beta. Okay. So clearly, in order to increase the signal efficiency, so I am increasing this part of this area here, because it is 1 minus alpha, right? In order to increase the signal efficiency, clearly the price to pay is also to increase the background efficiency as well. I mean, background efficiency is this, because by doing this, what you are just like trying is to have this to the right? So you move t cut to the right because you want to decrease alpha or increase the signal efficiency. But if you move this to the right, this cut to the right, then you are also increasing this area here that is being integrated. So it is this typical compromise when you want to, when you're studying physics, some data analysis of some experiment, that okay, you like move your cut in order to accept more and more signals, but then you are also swallowing a lot of background as well, right? So this is where to stop is something is part of data analysis, and you need to define what is the optimal point. And just in order to create a test, because you can do plenty of tests, right? So it's basically an infinite amount of possibilities of test statistics summarizing some data. But there is something very useful called the Neyman-Pearson lemma. Okay, and this lemma is telling you that the acceptance region, the acceptance of A0, okay? I am talking about T space. I'm now talking about the test statistics space. Given the highest power, is the region is the following region. The region where you have the PDF corresponding to the null hypothesis divided by the region, so divided by the PDF of the alternative hypothesis, where this is larger than some number C, where C is such that the integral of this, and this is the heavy side step function of this ratio, minus C, this is equal to alpha. So you define the significance of your test, and then once you fix this, you can find a value of C such that when the this ratio here is larger than C, you ensure, and this is the lemma, you ensure that the test is the one giving the highest possible power, okay? So let me now put a concrete example of that. So example, oops. So in this example, let's suppose you have a single observation. And this single observation X, so then assume it is Gaussian with a fixed variance, let's say. But I mean, and then I want to make a hypothesis about the mean of this Gaussian. So I have that X is given by a Gaussian, so I write it like this. But I mean, I have fixed my value of sigma. So then I want to compare A0 being mu equals 0 with respect to alternative hypothesis, which is mu equal 2, for example. So I want to discriminate between these two possibilities. And say in practice, what you do in practice, the Neyman-Pearson lemma is implemented with the likelihood ratio. So it is equivalent what I have written above about the ratio between the PDF of the test statistic. It is equivalent to the ratio of likelihoods of X, which is not the same, but it is equivalent, okay? So Neyman-Pearson lemma implemented as likelihood ratio. So let me just put this likelihood ratio, write it like R. So I am just saying that this is the likelihood of the null hypothesis. So this is just 0.1 divided by the likelihood of the alternative hypothesis, which is 2.1. And this should be larger than C, or some, let me call it T cut. Sorry, X cut. So let's choose the alpha equal, I don't know, 0.05. This is the significance of the test. So if I choose alpha equals 0.05, then, and this is a Gaussian, you know what, I mean, alpha is already defined before, so I'm just writing here what is alpha. But you have these numbers in tables, right? So if this is 0.05, it implies that X cut, you look at the tables and then you get it. This is more or less 1.64. Okay. And then you just compute the likelihood ratio. So compute the likelihood ratio means R equal to e to the minus X squared, and this is the exponential of the numerator, minus the exponential of the denominator, so it becomes a plus X minus 2 squared, right? And then the normalization is the same because I have considered the same variance for the two hypotheses. So you compute this is just e to the minus 2x plus 2. And this likelihood ratio should be larger than X cut, which is 1.64. So if you work out this, and then so you take the log, etc., and then you put X to the other side of the inequality, so you get this expression, 1 minus the log of 1.64, the natural log, okay, which is roughly 0.75. So the acceptance region is this one. And now I will measure my data, the observable, and then I will be able to say, okay, if X turns out to be larger than this, I reject my null hypothesis. And this is just a concrete example. There are many, but that actually captures most of the way that in which you implement this. Any question with this example? Okay, so imagine.
I have one question. So what happens if we assign prior probabilities to like a Bayesian approach?
So you are asking about a statistical test in a Bayesian approach?
Yes.
Yeah, I suppose that yeah, it is. I mean, formally, it is a. This is a question that formally is not. It's a bit ambiguous, but because what in the Bayesian approach you are. What is your null hypothesis here? What can be your null hypothesis in the Bayesian approach? Is so you are referring to, for example,
you don't consider the hypothesis as a random variable with some prior?
You do, yes, but then yeah, I will need to think on that. I haven't seen like statistical tests like this in the Bayesian approach. Of course, people do many things in their work, and they combine a lot of Bayesian and frequentist techniques. But like the purest way of presenting this is. Yeah, well, my confusion here is again about the prior. So if you have a prior, then you may start rethinking about what would be the strongest test. Is it the test giving you the highest power? Is it again something about the likelihood, or is something about the posterior, right?
Yes.
And that question, okay, I don't have an answer for this now. But it is, yeah, we need to think on that. Good. Thanks. Any other question? Okay. So I was about to say, so in general, you have not only one observation, right? So you have many. You have many observations. So let me just, and you have many observations of a random variable which is not even univariate, but you have a vector of measurements, let's say. And then you have a lot of observations, n observations. Then the way to go here is to again construct the likelihood of this. So the likelihood of null hypothesis here will be, okay, now you might need to make an assumption about independent and identically distributed data such that you can multiply all the likelihoods of every data point. For example, this, right? Well, okay, let me, okay, this is complicated because let me just refer to a univariate, but you have many observations of that. And then what you do is, again, to build the likelihood ratio with based on the likelihood, right? So you have another alternative hypothesis with its own likelihood, and then you just build the likelihood ratio, this test statistic, which is just the log of the ratio of likelihoods, okay? And this is typically like omnipresent in every frequentist test, frequentist approach. Okay. Of course, here there is a problem, no? So there remains a problem of knowing the likelihoods. I mean, knowing the likelihoods can be a complicated thing, right? So it can be like X can be highly dimensional, and then how do you build this likelihood of highly dimensional? You may think of building like multi-dimensional histograms and then trying to get the likelihood from there, like in an experiment, so you have a simulator, etc. So I mean, it is. There are many situations in physics where it is not at all easy to get what is the likelihood of the data. So how do you proceed? If getting the form of the likelihood is like I say prohibited, it's very expensive. Then what people do is to approximate. So the solution here is you approximate your TS. So instead of trying to build like the exact likelihood ratio, you approximate it by a function. So you approximate this by a function of X, right? And this function of X, and then you fit the parameters of that function. And then you fit the parameters of that function such that you maximize. So you maximize the separation between the two hypotheses. Between, let's say, this PDF and the alternative PDF. So what you want here above is that these two guys are as separated as possible, because that means that you are in an ideal situation where the background contamination is small, right? Ideally, if these two are completely separated, you know exactly what is the T-cut right in the middle, and then you don't lose efficiency of your signal, for example. So you try to design an algorithm for doing that. And actually, this thing, this whole idea can be rephrased or reinterpreted as a supervised learning algorithm, supervised learning problem. And the supervised learning problem in machine learning, then the idea is to classify. So you classify events or points, okay, coming from either one or the other hypothesis, 0 or HA. So in a way, you can think of a problem like this. So you have points here coming from one hypothesis, right? And then you have points here coming from another hypothesis. And then, of course, here, the idea is to try to get some discrimination, right? So if you are at the, imagine that this is H0 and this is points here are HA. So if you try to, if you estimate somehow this boundary, then points to the right of the boundary would belong to H0, and then otherwise would belong to H1. So you would accept H0, let's say. So in this region here, you would accept H0. And otherwise you would reject it. Okay. So this is the way to go. At the end, what we are doing typically is to approximate the test statistic having the highest power. This is what we are doing in machine learning at the end of the day. Okay, so any questions so far with respect to this?
I have one.
Yeah.
So in the example that we did before in the Niemann-Pearson lemma, so here we have only one observation, right? So, but if we have many, then we can define like T in a different way, and then we wouldn't calculate the ratio of the likelihoods, right?
Exactly.
But okay. But of something else, like the distribution of it. Okay.
Yes, exactly. And then you would see, and then you would see that. Let me think where I can put this. Okay, I will put this very zooming in here. You would see the following. Let me draw something that you will be familiarized with. So if this is a false positive rate here, and this is it 1 minus the false negative rate? I don't know how is it called now. Is it like a true negative rate? I mean, this is 1 minus beta, is what I'm saying. Then you would see that for a given value of, and this is actually alpha here. Okay, I'm talking about alpha and 1 minus beta. And then you would see that if you do one test, one possible out of the infinite many tests that you can think of, then you will get something like this. And then another better test will get something like this, etc. So you will have many possibilities, but actually the one giving the highest power will be the Niemann-Pearson lemma, the likelihood ratio. Okay. And this is just
in that case, for if we have many observations, then we will compare the joint likelihood.
Yes.
Okay.
Yeah.
Thanks.
And this is nothing but the ROC curve, no, the receiver operating. What? Remember, I don't remember the C. What is this? Characteristic curve that we see in machine learning that actually the classifier or the model performing the best is the one maximizing this. Okay, but this is nothing but saying what is the model best approximating the Niemann-Pearson lemma or the likelihood ratio, the true likelihood ratio that you don't know. Okay. Okay, good. Very nice. So in the last 5 minutes or so, I wonder if I introduce the other concept. Maybe yes. Yeah, I will do it. So if there is no more other questions, I will just introduce, and then we'll finish tomorrow with this other topic, which is goodness of fit. I mean, it's here. Okay, so what is this goodness of fit, and what is different with respect to the previous treatment that we were doing? Is the fact that in some situations you are not interested in comparing two hypotheses, but you are just interested in saying, okay, how good is my hypothesis, my H0, regardless of the existence of in consideration of any other alternative hypothesis. Okay, so this is just about just about agreement between H0 and the data, regardless of any possible different hypotheses. And the way to quantify this test here is, so they use the p-value. So the p-value, what is the p-value? Is the probability, of course, under H0 of obtaining a result in your measurement, in your data, which is as compatible or less with H0 than the one actually observed. Okay, so this is just like the definition of p-value. So let me just put an example here, a very quick example here. So for example, suppose you have an experiment, and in this experiment, you observe, I don't know, number of counts. You observe this, right? So what is the goodness of fit of H0? So now the question is, what is the goodness of fit of H0? And H0 is what? H0 is just one value of a parameter referred to the Poisson parameter, let's say. So I'm just assuming now that this n observed, that this random variable is follows a Poisson distribution. You can imagine this, for example, that lambda here is contains your parameters of your, I don't know, your model, your beyond standard model theory or whatever. This everything is contained there, and then as a function of all these parameters of your BSM model, you compute a lambda. This is the expected value of the number of observations, right? And then what is the goodness of fit of H0? That depends. Okay. Why it depends? So you have two situations, right? So imagine that you have here 0, and you have a observation here, and then your hypothesis is here. So if this is the case, then you can compute the p-value. Here, the p-value is just so go back to the definition, the probability of obtaining a result as compatible or less than the one actually observed. So if I am here, I have measured here, but my hypothesis here, this is to be as compatible or less means going in this direction. Because if getting farther away from my null hypothesis, I am less and less compatible, right? So in this case, what you do is to sum everything to the right of your observation, to sum all the likelihoods of possible values of n given your H0. And this is the opposite to what you get from the situation where your null hypothesis is actually a value, an expected value, which is actually larger than the one that you observe. And then if this is the case, of course, what you need to be to build the p-value in order to be as compatible or less is to go away from, again, you go away now from lambda 0, sorry. And in this case, the p-value is just the other sum, no? The sum between n equals 0 and n ops of the same thing. Poisson n times, given H0. particular example is, for example, I have observed 7 events. What is the p-value of lambda equals 3? Then, well, this is just from n equals 7 to infinity of Poisson n given 3. And this is roughly speaking 0.03 or so. Right? So, and this is a simple example coming from a Poisson variable, but then you have analogously the p-value for a Gaussian variable x. Then you have here your Gaussian centered at mu0. This is x, right? And then if x ops is here, then of course you need to make this integral in order to get the p-value. So that would be, in this case, would be the p-value would be given by this integral. Whereas in the other situation, you will have the other tail, no? The left tail. So here you have mu0, and if the observation is here, then you need to integrate this region in order to get the p-value. So this is exactly analogous. And we'll stop here because it's already 1, and then I wanted to continue with the chi-square test that we will discuss about tomorrow. Okay, questions so far?
I have a question, if I can.
Yeah.
According to the definition, then wouldn't it be possible also the symmetric possibility for the Gaussian? Like even if I move in this plot that you have on the left, the extreme right, then the compatibility would be even smaller, right?
I don't get the question, sorry. Yeah.
Like if you look at the plot on the left and say mu0 is here in the center, then you say, okay, the result is less compatible if I move to the left of x observed, but it would be also less compatible if I took all the area on the extreme right of the plot, no, where x is like near to infinite, or this region symmetrically.
Yeah, that's why I put the right plot.
Yeah, but so you I mean, why don't you consider both always?
No, because
I would expect some kind of function of the distance between x observed and mu0, like with some absolute value, just a distance.
No,
somehow.
because you have a hypothesis mu0, and then you unblind the data.
Okay.
Data a posteriori. Okay.
Mm-hmm.
So you put your mu0, and then if it is a Gaussian, so you will have a Gaussian center in this mu0 that you have chosen as your null hypothesis. Then you look at the data posteriori. What is the data telling you? Is it larger or smaller than mu0? And then you, I mean, I understand that you're asking is why in the computation of the p-value here, I don't consider something like here.
Yeah,
This
exactly.
is what you're asking, but I mean, I understand that going away, I mean, that this region is also going away from mu0, but where is the observation here? The observation is not on the right part of the, right? So the observation is not there. The observation is at the left of mu0. This is not like defined, no? So where do I stop integrating? I start integrating here or here or.
No, I say just wonder because with that definition, it seems that it would have been allowed. I mean, just less because this less compatible is, yeah, kind of not clear what is meant in this sense. It could be an allowed, in my perspective.
Okay, so you're saying that this definition doesn't exclude the possibility to have this integral as well.
Yeah, that's what I'm asking. It seems to me that it doesn't. But
no, but you need to refer to the data. This is what I don't get. I mean, you need to refer to the data somehow. So let's try to rephrase the thing with the Poisson distribution here. So that would be like, okay, I need to sum everything here, but also something here, right? It doesn't make too much sense, no? To start also considering this other tail, no? So you are referring to the p-value of a null hypothesis with respect to some observation, right?
Okay.
And then you need to refer to the other observation. So you have the likelihood if you want. Let me see if this comment is clarifying. So you have the likelihood of an observation given a hypothesis. And then this is a definite number given by your observation and your parameter, the value of your parameter. So you know how to compute the Poisson of n ops given x0, or you know how to compute the Gaussian between x ops and mu 0. That you know.
Mm-hmm.
Now I have the likelihood of this observation with respect to my null hypothesis, and then in order to construct the p-value, I am told that I need to consider to sum the likelihoods of other possible data compatible or less than this. So then here I don't see why this part should enter, because there is no data is not here to start with.
Mm-hmm.
Yeah, I don't know.
Okay.
Okay.
Okay. Thank you.
Any other question here? Okay, if no more questions, let us close here, and we meet tomorrow the same time for the other lecture. Okay, so we continue with the statistic, the chi-square we will discuss tomorrow. Okay, so thanks a lot, and see you tomorrow.